Two. So welcome everyone to this week's Origins colloquium. It's actually the second colloquium this week. It's a pleasure to have Michael Fellhauer visiting Chalmers University today. Mike received his PhD from the University of Heidelberg in 2001. He had postdoc positions at a few institutes. Let me remember now. Kiel and Edinburgh and Santa Cruz and Bonn before starting a faculty position.
No, Cambridge came before.
Cambridge as well, somewhere in there.
And then
before starting a faculty position at University of Concepcion in Chile in 2008. And there he's been leading the theory group that has, we were chatting earlier, is one of the biggest in Chile and even South America. Mike's expertise is in dynamics, in particular n-body simulations of galaxies and star-forming regions. And today he's going to tell us about a model for forming dwarf spheroidal galaxies. So welcome.
Thanks a lot for having me here. So as you heard, the talk today will be something completely different, not about massive black holes, not about star-forming regions, but about dwarf galaxies, and especially the dwarf spheroidal galaxies. So you see here on the right, that's one of the more massive dwarf spheroidals of the Milky Way, which is known since the 1930s. But most of these systems are really, really small. We are talking on the faint end about 300 to 500 stars in a galaxy that's Segway 1, up to maybe 10 to the 5 or several times 10 to the 5, but usually in the order 10 to the 4 stars. So they are not visible to the naked eye. They are not really observable like that one you see in the picture. They are found by counting overdensities of stars in big surveys like SDSS or the Dark Energy Survey and Apogee and whatnot. So I will have this picture here in there we go, a little bit bigger. This is the overview of all spherical or elliptical, or let's say pressure supported systems we know. So at the low end, in black, we have the globular clusters, extended a little bit to the right by ultra-compact dwarf galaxies, where people don't know, are they just strict nuclei or are they just the extension of the globular cluster sequence to higher masses? And on top, you see coming from the right down, that's the sequence of elliptical galaxies. And this sequence has a turnover, if we come to the dwarf elliptical galaxies, which have 10 to the 10, 10 to the 9 solar masses. And following that sequence, we go to really, really small systems, low mass systems in stellar mass. That's the dwarf spheroidals, which I will talk about today. And with the recent discoveries, we've extended that sequence to the really, really, really faint and small end, at least around the Milky Way. So how do we form those really small, low-density objects? So standard cosmology says small objects form first, and then we build larger objects out of the small ones. So maybe those dwarf toroidals are really the remnants, the last remaining ones of the first galaxies which have ever formed. And so there are models which are attributed of a galactic origin, and on the other hand, you have the no dark matter models, where you see them as blobs of stars, which are remnants of destroyed star clusters or tidal dwarf galaxies. So objects which formed without dark matter, not within a dark matter halo, as secondary objects after a big interaction of the mother galaxy. And models have shown that those disrupted objects still have a central blob which can stay coherent for giga-years, even though they are not bound to each other. So that would be the no dark matter models. Our group worked on this field as well, have shown that it's possible, but most people don't like that because that will put a strain on the missing satellite problem again. But in principle, it's possible, but that's not the topic today. Today the topic is the two galaxy origin models. We have the standard idea how dwarf toroidals form, which are the models by Maya and Dongia, that dwarf toroidals are the disrupted remnants of little disk galaxies. And we can see here, these models work quite well. So you have a little disk falling into the big halo of a galaxy like the Milky Way. The gas gets stripped, then stars get stripped, then with tidal forces of the Milky Way potential, you destroy not the dark matter halo, but the disk, and you are left with a low mass, low density object at the central part of the satellite halo, which looks like a dwarf toroidal. Or because dwarf toroidals are also known far away from big galaxies, there are the models of Elena Dongia and her group. You can get the same effect if you have multiple little disk galaxies of small sizes which interact with each other. And so you could form dwarf toroidals by interactions between two small disk galaxies as well. All these models, these models need are higher mass objects, which then transform into a low mass object. And they need interactions. And our idea, which is not a standard model, but which to me seems more reasonable, is why not form those objects exactly the way how we see them today, as little low density blobs without any trace of rotation, with pressure supported systems. And that's exactly what our model tries to do. And to give some criticism to those kind of models, on a recent conference last year, I spoke with observers and theoreticians who do big cosmological simulations. And the observers told me they haven't seen any small disk galaxy below a stellar mass of 10 to the 8. And the cosmologists who do big cosmology simulations say exactly the same. So those models which rely on small disks of 10 to the 6, 10 to the 7 are a bit questionable. So, okay, so let's have a look what our model is about. Those are our dark matter-free models, just to mention that we have it here. This is the dissolving star cluster model, and please excuse the term star cluster. We say this is a star cluster even if it has just a few tenths of solar masses and would be classified by an observer as association or a group of stars. So everything which is in a clump we call star cluster, just to have one term over. So we start out with a dark matter halo, and we assume that in this dark matter halo we get infalling gas, and this gas forms stars at the center, but not evenly distributed, but in little clumps, in little associations, in little star clusters. Yeah. So of course these star clusters have bulk velocities. All those stars forming in the same group are moving around in this dark matter halo in more or less the same way. They have individual motions within the little group, of course, but they have a bulk motion which put them on a regular orbit inside the central part of this dark matter halo.
What is the depth of the potential here? What is the escape speed of this halo?
This depends on how we scale our model. So if we do models for Segway 1, then it's scaled to the assumed dark matter halo of Segway 1. If we do models for something like Fornax or Sagittarius, that's much higher.
Can you give us a rough numbers here for such?
Escape speeds are in the tens of kilometers per second.
Okay.
And the internal velocities are in the below 1 kilometer per second, or in the order of a few, depending on how big we make each star cluster in quotation marks. Yeah. So of course, as the whole mass, stellar mass, is just 10 to the 3, 10 to the 4, 10 to the 5. So this is low star formation efficiency. And so these objects dissolve and spread their stars along. So if this object has an elliptical orbit like that, the stars would be spread in a ring-like feature along the orbit with time. Yeah. Okay. And if you take all of them together, you get some kind of a blob, a low density blob of stars in the central part of the dark matter halo. And that's what we propose how those dwarf spheroidals form. Okay. Good. Now, can we prove one or the other scenario? Yeah. Well, what we see in real life is those low density blobs like Bootes 1 have disturbed contours. So could be that they are tidally disturbed. That would be, but if they are still very well within a dark matter halo, those tidal disturbance would point to a rotation origin, so like a disk galaxy. Yeah. Because that you can disturb because of resonant tidal stripping, even though they are well within the dark matter halo.
We might need to come back to that point.
But what you also see is that maybe the densest part is not right in the center of the outer contours. What else can you see? Yeah, contours which are not perfect ellipses. They have twists and turns. And maybe you see even secondary density peaks, like, for example, here in Hercules 1. And, well, this could be all just bad statistics, because we don't see all the stars. We only see the brightest stars, RGB stars, for example. And so this could be just a sampling effect. But if you believe it's real, this is, for example, the contour map of one of our objects. And I like psychedelic colors, so please bear with me, and you have to watch these psychedelic colors. But you see, there are different density peaks. We have contours which are not ellipses. So we see exactly the same in our models as we see in observers, in the observed dwarf toroidals. Only that we have larger than life simulations. We do the simulations with a particle mesh code. So we don't simulate star by star. We simulate with millions of phase space elements. So instead of one star, we have like 100 phase space elements doing the same thing. And so you get a much better statistic out of it. So yes, we see strange contours, secondary density peaks, S-shapes in some models, as we would have tidal disturbance. What we also see is different density, different peaks in radial velocity. So here we have a region where the stars are having a bulk motion compared to the complete motion of the dwarf satellite, which is a little bit faster, so receding from us here, coming towards us. You could say this is a sign of rotation, yeah. But you also you have something red here, something blue here. So we see some kind of bulk motion, which is much less. So it's within the bound velocity of the dark matter halo. And do we see that in real life? This is Fornax, where this is the dwarf toroidal of the Milky Way, where we have the most radial velocity information of single stars, and until now, more than 2,000. But in the central part, there's only about 500. And no. So with just plotting mean motion per pixel, we can't confirm or reject our model.
But there is structure in there which looks real, or is that in the noise? Because you said it's a few kilometers.
Yeah, it's a few kilometers per second, so it might be, it might be not. It's not statistical relevant. If you do the histogram, it's not significant. But maybe, yeah. Therefore, no with a question mark. But what we saw, if we lose the 2D information and just do radial nice rings and determine the velocity dispersion, what we see in some of our models are strange kinks Yeah, and wobbles. So this is going velocity dispersion at some radii going a little bit up and then down again, or here a little dip. Yeah. And if you look at the real data, and these are the big ones where we have really a lot of velocity information: Carina, Fornax, Sculptor, Sextans, Draco, Leo 1 and 2, and Ursa Minor. And yes, there are kinks and wobbles in the measurements, which are within the error bars, so you can still fit a smooth model through it. But it was a hint at that time when we first introduced our models. It was a hint that we see something similar, and some of those things might not be just error within the error bars, but real. And that was the situation until recently. So the project was done around 2020. It took quite a long time until we published the paper. We got velocity information, new velocity information observed in Leo 1 about, my student had about 900, almost 1,000 radial velocities in Leo 1. And he got access to a code which looks for stellar streams or remnant rotation in radial velocity data. So it looks for groups of stars which have more or less the same position and more or less the same radial velocity. And you can even add that they need to have more or less the same metallicity, which if you form stars in as different groups and star clusters, you don't expect all of those groups to have the same metallicity. You would have some metallicity spread. And this code beacon is even intelligent enough. If it sees another group on the other side with exactly the opposite velocity, it puts the two groups together as a double-sided stream. So you can see groups of stars which have this similar motion, some kind of rotating pattern inside of a much larger data set. Okay, so we can use that code on one side on the observational data, and on the other side on our simulated data. Yeah. And well, as I said, we have larger than life simulations, and our data is perfect. We have exact positions, exact velocities, exact metallicities, everything. So of course, we need to reduce our data. So out of millions of information, we randomly draw about 1,000, as we have in the observations, and then we have to convolve these good information with observational errors, and then we see what comes out of it. So in our simulation, 100% of the stars are belonging to streams, because that's how our model was set up to be. Yeah. And yeah, we can recover about 80%. That's the red line. And this MCS is the minimum number of stars we require to be together to be called a stream. Yeah. And if you increase that number, you reduce the number of streams. But correctly recovered, we do about a quarter. So 20 to 30% are correctly labeled to be from the same original group or star cluster. Yeah. What we see, we get, but on the other hand, if we use data which has no streams, so we can build up an object with just random velocities, yeah, like a pressure-supported system, like a plumber sphere, and use a beacon on that as well. And what we see are these fake, not real streams have a dependency on MCS, on the minimum number of stars we require to build a stream, which is an exponential decrease. Yeah. And what we see in our simulation, that's the green and black, that's no streams whatsoever. It's an exponential decrease. And blue is now a simulation where there should be 16 streams, which is made out of 16 streams. And remember, we have a 20 to 30% chance to catch the stream. And what you see is you have it's completely swamped by just random streams which are not really present. But if you go down, if you increase MCS, at one point, those blue dots are sticking out, where the fake, the streams have that low number that this 4 or 5 streams which you should detect really make a difference and stick out.
Let me clarify. These are internal streams in this little galaxy.
Yes.
Internal streams.
Internal streams. Yeah. So this, even if error bars are overlapping, but this feature, this is typical that there is something. You can't. You measure here 10 streams. You still, if it's not a simulation, you wouldn't know which of the 10 streams is real and which one is just a false detection. But you see, it's more than you would expect by just this exponential decrease.
And you include binaries in the models or not? Are there stars in binaries? And does that affect things?
It could affect things, but it should make it worse. And we don't have binaries, so it's not corrected for binaries. And if you want to have 10 or 12 stars, this is not a binary effect. Okay, so remember this with data which is as bad as observed, we can get a detection rate of 20 to 30% max. Yeah. And there are a lot of false positive detections, but they decrease exponentially with this parameter, the minimum number of stars we require. And if there are real streams, then we should see a feature like the blue dots. So they follow the exponential, but then they stick out. And at one point where we increase MCS to more stars than that actually are detected in that real stream, then it drops back into the false detections. Okay. And here, once again, you see in green and black, that's a simulation of no streams whatsoever. So the exponential decrease. And now in red, you see the observed data of Leo 1. It has no error bars because it's just one object. Yeah. And what you see is exactly that it's sticking out.
How many stars are in the Leo 1 in the database?
1,000.
Uh-huh. Mm-hmm.
So there is something, yeah? Even though we can't prove that, okay, at MCS equals 10, we have about 14 streams. We have no clue which one of those 14 are real and which is just a false detection. But it definitely says we are above what we would expect from pure noise.
And the selection is based on kinematics only, spatial kinematic, not metallicity.
It's only based on kinematics. We left out metallicity.
You could check then metallicity.
Yeah. Okay. Then we can determine the angular momentum, or at least the projected angular momentum of those streams. If they streams like this, or like that, or like that, and the projected angular momentum vector are pointing in all kinds of directions in the simulations, and they are pointing in all kinds of directions in the Leo 1 data. So what does that tell us? This is not a sign of remnant rotation. So if you have a destroyed little disk galaxy, what you would expect is if there are still traces of the original rotation, you would expect that those arrows are all pointing more or less, not exactly in the same direction, but more or less. And then on top of that, you have some the false positives, which also can point in any direction. But you should see a preferred direction, yeah, and we don't see that. So what I would suggest is, even though Beacon was designed to find remnant rotation, and also our co-authors want to have remnant rotation, and that's why they delayed the paper like hell. But this is what you get from a destroyed disk model, and my student ran models like Maya and Dongia did before, and yes, I don't have the original data with me, but it looked like that. And this is what we get from Leo 1, and that's more in accordance with our dissolving star cluster model. So maybe meanwhile you can do better with machine learning and more sophisticated algorithms taking the metallicity into account to find coherent motion in large or medium-sized data sets. But I find it quite convincing what Beacon did with all its restrictions, that it confirmed our models.
Yeah,
quite well.
If you had you do have tidal perturbations from the Milky Way and so on, and maybe other things. If that completely destroyed the disk, and then everything was just sort of random streams,
then you would see just random degrees.
Right.
So
the disk model only survives if everything is
so
randomized.
if everything is just random motion, so each star does its own little
But do you expect that
orbit, then you would get this exponential decrease in false positives.
But do you expect the disturbances, the external disturbances, to destroy the disk or not? If there was a disk, it would still be there.
It would destroy the disk effectively, yeah. But if there is some remnant rotation, then it would show exactly the same pattern. You would measure, but on so at one point, if you increase the number of stars you require to be a stream sufficiently that the number of real detections added to on top of the false positives should make something like that. It's still, you can still argue, yeah, well, there is, you expect 10 to 12 false positives, and you get you measure like 16 plus minus 3 real ones. That's within the that's within 1 sigma. The error bars are overlapping, so this is statistically speaking not significant. But just to have this feature shows that there has to be something, and we are not the only ones. So this is from a paper of Del Pino from 2017, and they wanted to find rotation. They designed beacon to find rotation in the Fornax data. And Fornax is the one which has more than 2,000 radial velocities. And if you look at, you see the exponential degrees of false positives. They also found that. And you see the black data points. And you see here, this is the sweet spot where the real detections stick out. Yeah. But, and they did the same analysis of projected angular momentum. And then they concluded maybe Fornax is the superposition of two little disks which collided in the past, and therefore you have a more random distribution of projected angular momenti. But I would say, why complicated explanations if you can explain it much more easier by just you formed stars in little blobs and groups, and they moved around the central part of the dark matter halo and formed a blob which we call dwarf toroidal galaxy as we see it today, and it stays like we see it today. Okay, with that, I'm at the end of my talk, and thanks for listening.
Great, thank you very much. So, any time for questions? I've been interrupting too much, but please, if you have a question, raise your hand online or or here. So, any questions for Mike?
I kind of have a question.
Yeah.
You said that these cluster with some radial velocity eclipse around in the halo, right? So does your simulation take into account that if they are eclipsing with some radial velocity, and does the radial velocity decreases with time?
Oh, sorry.
Pre-
This.
Yeah, so you said that they rotate with a particular radial velocity around in the halo. So does this simulation take into account that the radial velocity might decrease with time?
No. Well, it's an analytic halo, so in the simulations it doesn't. But yeah, I think dynamical friction is not that effective on stars which are spread around and.
You're talking about the effect that the dark matter halo of this system might be decreasing in time?
Yes.
Yeah, so you have fixed dark matter mass, do you?
Yeah.
Yeah, at the moment, right. But do you have external tidal perturbations on this?
No, it's completely in isolation.
Yeah.
So each little model is its little universe with one dwarf and nothing else.
But to order of magnitude, the external perturbations, I guess this is what I was asking. Are we in a regime where they are important or not that important? Because to destroy your streams.
No, you still are looking at a pressure supported system. So pressure supported system, if you throw it into the tidal field of the Milky Way, for example, you will lose some stars. There's always some stars randomly picked, which are in resonance with the tidal force of the Milky Way. But not like at this galaxy where there is a whole ring of stars which has exactly the correct rotation velocity, which then is in resonance with the tidal force and gets ejected. So with a pressure supported system, you really have to strip first the dark matter halo before you really affect on a big scale the luminous component.
I'm not really talking about stripping the stars or anything. I'm just talking about mixing the streams so that in the end.
Or they do it. I think they do it much more effectively by themselves. So you see, it's not a Keplerian potential. So this group of stars doesn't do a nice ellipse of an orbit. It does a Rosetta.
But you
have some kind of ring-like or cloud-like structure. How the stars.
But you are running for, you said 10 gigayears or 12 gigayears, and your streams are preserved.
Yes.
Right. So I guess my question is the external perturbations then that you don't have at the moment, you don't think are at a level that would destroy the streams, because they're not destroying themselves at the moment, or at least you are preserving some real streams in your data. Right.
So if you have no perturbation in our simulations, the streams are visible until today. If you run Beacon on our simulation with the full data set, then it detects everything.
Okay.
If you put 16 little objects which dissolve, it detects 16 streams. As I said, if you take as many data points as Leo 1, then and convolve it with observational error, then the detection goes down to 25%.
Okay, I have other questions, but if people want to ask something, please jump in here. Otherwise, I guess my next question was the metallicity spread that's in these like Leo 1. I mean, to find a real stream, you have to, I suppose you should be now checking the metallicity clustering of the streams. So can you say anything about that?
The thing is, as we are not doing star formation or any hydrodynamics, in our simulations, we don't have metallicities. The thing what we can do is
But
paint the stars from different objects like red, green, blue,
Sure.
yellow, and say, well, if we assume this kind of star formation history and that kind of enrichment
I
law,
mean, in the data,
then, yeah.
in Leo 1's data itself, you know, at MCS of about 20, was it about 20 that you
Yeah.
think you've got the highest chance of finding a real stream? So perhaps you can pull up the Leo 1 data.
It's around
10, sorry.
8 to 10.
Yeah. So then the question is are there clusterings in metallicity of those or so?
Yes, as well.
But has anyone looked for that yet?
Yeah, we did. And more or less, they also have in the real data, they also have similar in streams, similar metallicities with some outliers. So yeah, but
Well, many of them would be false. So
yeah, so the metallicity would be all over the place. Yeah.
So, but some of them are real. I guess if they're real, they should have the same metallicity. But you always have some contamination.
Yeah.
So you can always explain outliers, but it's more whether the clustering properties of metallicity space would be greater than random. So that's I guess that's the question.
If those, yeah, some streams have. I mean, this is the initial requirement. Yeah. So it has to be 8 stars to be a group. But then once it's classified as a group, the algorithm looks around. If there's another group which is similar, so then they get put together, or some stars around that group have the same pattern, they get also included. And then once that's established as a one-sided stream, the code looks on the other side if there is exactly the opposite. And then those 2 streams get put together as a double-sided stream. So
now let me just try and understand. So in some of these models, everything formed in a stream, but you're only picking up. It seems like a lot of streams have been destroyed because very few stars are in the streams. Am I right here? By what fraction, when you do MCS of 10, you've picked out, looks like you've picked out 14 streams. So that's 140 stars, is it?
no, so
that's 10
one of the this is just the minimum number required before the search algorithm sets in and looks around.
Okay, so what fraction of stars are put into those 14 streams in that case?
It's another less than 20%.
Yeah, but that's another metric that you can compare to the models.
Yeah. But it still goes within it's within the correctly recovered 20 to 40%, depending on how strict you are.
Okay, then. Any other questions for Mike before we finish? Okay, if not, let's thank Mike again.